Good morning and welcome to everybody. It's a great pleasure to go on with the IQTC seminars. This is our first seminar in which we will be hybrid, so we have people on site and other people via Zoom virtually. So also welcome to those who are via Zoom. It's a pleasure for me to introduce Dr. Alba Cervera. She is a senior researcher at the Barcelona Supercomputing Center, just at the other side of the diagonal, let's say. Alba obtained the PhD in this house on quantum computation and quantum information. Also a master in particle physics. When she finished, she moved to the University of Toronto as a postdoc at the Alan's Spuro-Guzik group, who is one of the top names in this field of quantum computing. She has just returned at the Barcelona Supercomputing Center, and since October 2021, she is coordinator of the Quantum Spain project that probably you have heard on the news, which is an initiative to boost the Spanish quantum computing ecosystem and the quantum computer at the Barcelona Supercomputing Center. She's main research interest is in quantum technologies in general and quantum computation in particular. She has worked on quantum information foundations, multiparticle, entanglement, and particle physics. Now she's mainly focused on discerning near-term opportunities of quantum computation and the synergies between quantum physics and artificial intelligence. And she's currently working on noise intermediate scale quantum algorithms and high-dimensional quantum computation. So welcome, Alba. She's also very active in outreach activities. She has participated in different media events, so you can follow her. She's even very active in Twitter. So the floor is yours.
Thank you very much, Jordi. Actually, I defended my thesis in this particular room 2 years ago. So it's the first time that I come back to my faculty, and it's a big coincidence. I'm very happy to come back in this particular room. So I was here 2 years ago defending my thesis on quantum information. So many things has changed though. So, okay, let me talk without the mask and set the timer. Okay. So today I would like to present this what is noise intermediate scale quantum computation and what are one of these main applications which are related with chemistry. So I believe that you might find it interesting. This will be a very broad talk about this subject, but it will be a technical talk. But I will give a talk about quantum spin project and more, general talk about what is quantum computation. Whoop, doesn't work. It doesn't work. Okay. Okay. No. It will be a colloquia organized by the ICC, the Institute of Cosmic Science in this faculty, and this will be a more general talk. So in this particular one, this will be a technical one, although the beginning of the talk will be more general to put everyone in the same page. So this is the outline of my talk. I will start with a brief overview of what are quantum technologies, what is quantum computation, and then I move to the state of the art that is also called noise intermediate scale quantum era. So this is the name for the state of the art in quantum computation. So that's why maybe most of you have heard about it, and it includes many kinds of algorithms, many kinds of even quantum computing paradigms, and I will talk about one particular one, which is variational quantum algorithms. And inside of these variational quantum algorithms, you can find the variational quantum eigensolver, which is one of the first proposals for this kind of algorithms that opened the field to this noise intermediate scale era. And it was proposed by my former boss, Alba Spuro-Guzik. And the main applications of VQE is precisely chemistry, although it has been extended to other fields like condensed matter physics, for instance, or even quantum machine learning, as I will mention briefly. So then I will briefly present what is the meta-variational quantum eigensolver, which is one particular proposal that we work on in Toronto, and which is a mixture between variational quantum eigensolver and a quantum machine learning algorithm. And then I will present one of the main tools for quantum computing, which is quantum programming, and in particular, Tequila language that we develop in our group, which is particularly suited for this noisy intermediate scale quantum era, and also it comes together with chemistry backends, with quantum computing backends, and it put many things together. So let me start with what are the quantum technologies. We are now in what is called the second quantum revolution. The first quantum revolution is considered during the second half of the 20th century, so during the 50s, 60s, etc., because it's when we discover how to use the properties of quantum physics to build devices like the GPS, like the transistors, like the nuclear resonance, etc. So we discover applications related with quantum physics. So during these years, people realized that to study quantum physics at a next level, so study quantum systems, it's not enough with classical computers, because the Hilbert space, the space for the simulation, grows exponentially, as probably some of you know. It's time that you want to simulate a big molecule, or it's time that you want to compute something related with quantum physics. So that is why people realized that we will need a device that has the properties of quantum mechanics in order to study this kind of systems. And this is the first proposal for quantum computation in the 80s by Richard Feynman. But together with that, we also have other things. We have quantum sensing, quantum communications, quantum computation beyond the quantum simulation perspective. So in the end, what is quantum, this second quantum revolution, is a mixture of quantum mechanics, information theory, and then the main applications that we are starting to realize are these three ones: the quantum computing, sensing, and communications. So of course, I will only focus on quantum computing, but I will to emphasize that there are these other kinds of quantum technologies. So what is a quantum computer in big terms? So it's a device that processes the information in a quantum mechanical form. And to be clear, it's not fully quantum. The quantum computer is composed by a classical part that controls the hardware, and the hardware is the quantum part, the purely quantum one. So in the end, the software, we program a quantum computer with standard computers. We send some set of instructions that alter the hardware, and this hardware is the one that has the quantum mechanical properties. And then the result of the computation comes back to our computer, and we post-process that, we analyze the result, maybe we start again the loop, and that will be a very important part in these variational algorithms, etc. So in this hardware, we have what are called qubits, which are the minimal units of quantum information, like as the standard bits. And this is the idea. So bits have 0 and 1. There are two states that are well defined, but qubits can be in a superposition state because it obeys the same laws of quantum mechanics. So that's why we can have 0, we can have 1, but we can have a superposition of 0 and 1. And the same will happen each time that we add more and more qubits into our computation. We can have things like entanglement that will be very important for this quantum computing advantage. So in the end, these qubits store and process this information, and they can handle exponentially more information than the standard bits. So the idea is that we need the order of 2 to the power of n bits to simulate n qubits. And that is why it's so difficult to simulate quantum physics with the standard computers in the end. So this is one of the cores of why exists this advantage for simulating quantum physics, but it's not the only one. People discover that if we assume the properties of these quantum bits, we can find new complexity classes. And this is related with which kind of problems can be solved efficiently with classical or with quantum computers. This is very important for computer science, and this shows that there are problems that not even with quantum computers we will be able to solve efficiently, but there are some of them that we can. And one of the main examples is the factorization problem that is related with cryptography, and that's why quantum computers became so famous, although we need super big and powerful quantum computers for that, and we are not there yet. But it is important just to stress out that besides quantum simulation, we also have other kinds of applications for quantum computing that have nothing to do with simulating quantum physics. So what is the state of the art in this quantum computing world? It's called the noisy intermediate scale quantum era. And the reason is because quantum computers nowadays, they are prototypes. They are composed of between 50 qubits, maximum 120, and it was achieved very recently by the company IBM. But these qubits, it's not only a matter of how many we have, but it's a matter of how good are they. And the properties of these qubits are not perfect. They have noise, and that's why it's called noisy. And that means that there are some quantum algorithms like the factorization problem or other kinds of quantum algorithms that cannot be run in nowadays quantum computers, because we need perfect qubits to do that. To achieve these perfect qubits, we need what is called quantum error correction. And to apply this quantum error correction, we need hundreds and thousands of qubits to simulate or to have one perfect logical qubit. That is why we are super far away for that yet. But besides this drawback, we still have something that is powerful. So we have a machine that we can control individually each qubit, and we can perform some tasks that not even classical computers can. And this task doesn't have any particular application yet. And these are these two main experiments: the quantum supremacy using a superconducting processor and carried out by Google AI, and the quantum computational advantage using photons. This is from the Chinese university. So they prove a particular simulation with a quantum computer that cannot be reproduced with a supercomputer, not even if we have 100 years of computation with this supercomputer. It's basically scanning a random distribution, so it doesn't have a particular application yet, but it's just a proof that we have devices that work pretty well, and they are powerful in some senses if we compare them with classical computers. So the question is, we don't have good quantum computers yet, but can we do something with these kind of machines, the ones that we have now? And the answer is, we believe yes, we can try to find applications with these noisy devices. And first of all, it's a good trial field to study and develop new quantum algorithms, to try to search proof of concept ones, etc. The other is, of course, it's a search into quantum advantage, into finding this application that will revolutionize completely our fields. And the other is because it's a step towards this fault-tolerant quantum computation with logical qubits that are perfect, etc. So in the end, it's be prepared for this next generation of quantum computers that I personally believe that there will be there at some point. So inside of this super big NISQ paradigm, there are many kinds of quantum algorithms and many kinds of strategies that people are trying to figure out how to obtain some advantage from these devices. And one of the main candidates are these kind of algorithms that are called variational quantum algorithms. So let me explain how they work in big terms. So these algorithms are also called hybrid quantum classical, and you will see why, because it takes the best of both worlds. So the hard part of the computation is carried out in the quantum computer, and the simple one or another kind of computation is carried out in a classical computer. So we start with some initial state that we introduce in our quantum computer, and then we apply a set of quantum gates. These quantum gates will depend on a series of parameters, and these parameters can be fine-tuned. The reason is, if we know exactly which kind of circuit we want to apply to simulate something, theoretically, maybe we need this kind of quantum gate, this other kind of quantum gate, and so on and so forth. But what happens if these gates are not perfect? So the result of the computation will not be exactly the one that we expect. So the idea of this kind of parameterized quantum circuit is to offer some fine-tuning into this quantum circuit. So we can find what is the particular parameter that we need and not the theoretical one, so we can adapt. So once we run this circuit, we have some output state, and we compute expectation values with this kind of state. So as you know, with quantum mechanics, we cannot observe the wave function, but we can obtain expectation values of some operators. And for instance, one of the main examples of quantum operators is the expectation value of some objective that can be a Hamiltonian, that can be encode, for instance, a molecule, or a spin model, etc., or even an optimization problem, as happens with quantum machine learning. But in the end, we compute some expectation value, and this gives us some upper bound of the ground state energy by the variational principle. So the idea is, okay, we use this value and we introduce it into some minimization subroutine that will try to find a new set of parameters that update our quantum circuit. And we repeat the process again. So after we repeat the process multiple times, we hope to converge to the ground state or to a good approximation of this ground state. So in the end, this part of the bottom is a classical optimization. So we need a classical computer close to the quantum one, so we can find this new set of parameters and search for the optimal parameters of the circuit. and eventually converge. Of course, many things can happen. So maybe we don't converge, maybe we get trapped in local minima, etc. But this is the main idea of these variational quantum algorithms. So let's see how can we construct this quantum circuit. This is the big question. So this is very nice, but okay, how can we design the quantum circuit in the first place? Because if we know in advance, we probably know how to solve the molecule in the first place. So this parameterized quantum circuit, there are many techniques to try to figure out how can we find it. But the idea is to, so first of all, we need to find the unitary operation that will be composed into basic quantum gates. And this is the parameterized quantum circuit. So this unitary operation could be super big, but in the end, the important point is we can decompose them into small quantum gates. So we have a receipt to construct it. As I said before, we have some assumptions. First of all, that there exist these parameters to approximate the ground state. So if we propose a circuit ansatz that doesn't contain or doesn't explore the full Hilbert space, we can get lost and we can never achieve the ground state energy at all. So we have to be very careful with that. And of course, this parameterized quantum circuit has to be able to explore different solutions and to encode the correct solution. Otherwise, we will end up in some random point in this exponentially big space. So as I was saying, how can we design this unitary operation? There are many techniques. We classify them as the problem-inspired and the hardware-inspired. So the problem-inspired are the approximation of the solution by construction, and I will show exactly how can we do that with the variational quantum eigensolver. So they are inspired by the problem. So we can obtain information from the problem and try to find which quantum circuit can approximate or potentially approximate the solution. But the problem is, in general, this kind of ansatz that require a lot of quantum gates. And this is not feasible sometimes to implement in our current term quantum computers. So that's why in some cases they are not useful at short term. And that's why people propose the hardware efficient ansatz. So we know how are our quantum computers, we know that which qubits are connected, which ones work better than others, etc., etc. So we can try to design a quantum circuit that adapts to the technology that we have at hand. And these are normally proposed into different layers that we repeat over and over as a neural network, and we hopefully end up in the solution. But what could happen is that maybe it's an heuristic ansatz, so maybe we don't end up in that solution, and our solution is in a super particular place in the Hilbert space, and we can never arrive with this kind of circuit. So that's why it's good for experiments, but maybe it's not good for the theory. With the objective function, as I said before, it could be a Hamiltonian that encodes a molecule, but it could be many other things. We compute the expectation value of that. And to measure that, we need to translate our Hamiltonian into what is called Pauli strings. And these are the things that we can measure in our quantum computer. That means that if we have a Hamiltonian and we translate it into these strings, for instance, I will show you later an example using a Jordan-Wigner transformation or similar. What happens is maybe we have a lot of elements in our Hamiltonian that we need to compute an expectation value for each of them. And that's why we still need to use approximations of our Hamiltonian, because we cannot handle an exponentially amount of terms. Otherwise, we don't have any potential quantum advantage at all. But besides these problems that are descriptions of some system, we can also encode other kinds of problems. For instance, the fidelity, which is the distance between a quantum state and our target state. And this is used for quantum machine learning, for instance. So we are trying to find a particular kinds of states. And as a cost function, we use the distance between the state that we generate and the target state that we want to find. And finally, the part of classical optimization, as I said before, it is a classical part. So we need a subroutine that is classical in our standard computers. So what people think at the first sight is, okay, let's use gradient descent. So we need to compute the gradients of the circuit for each parameter of the circuit. That could be that if we have a lot of parameters, there is a lot of measurements, so that's not very practical either. And that's why people are trying to figure out how can we find other kinds of approximations, other kinds of ways of computing different gradients with only one measurement, or even use methods that are not related with gradient descent, that are gradient-free, like genetic algorithms, reinforcement learning, etc. So this is also a very active field of study how can we optimize the parameters of the variational quantum algorithms. Oops. It doesn't work again. But not my, okay, no. Okay, let's see some applications. So let's try to figure out something more specific. So the main one, as I said at the beginning, one of the first algorithm that was proposed with this kind of a structure was the variational quantum eigensolver. The other one was the QAOA algorithm, which stands for Quantum Approximate Optimization Algorithms. Both of them are very similar because in the end, they are this kind of variational quantum algorithms. But the BQE was particularly targeted to solve the electronic structure problem. So let me summarize this problem, and I'm not a chemist, so this will be a very brief approximation of what kind of problems we are trying to simulate. So apologize in advance if I say something that is not very precise. So as you know, in the Born-Oppenheimer approximation, the Hamiltonian of our molecule or atom has two parts, the one related with the nucleus and the one related with the electronic structure. And we are interested in the electronic structure one, which has more or less these terms, the kinetic energy, the interaction between electrons and nucleus, and the interaction between electrons. So this is the theory, but we are interested in seeing what are the solutions of this Hamiltonian, what are the wave functions of the electrons of this Hamiltonian. So a single electron wave function are the orbitals, but once we are considering different orbitals, we need the Slater determinants, we need to compute all these parts. This becomes more and more cumbersome, as you know. So what people usually do is to move to the second quantization or the focus state. And in terms of quantum computation for our purposes, we like to write things in this way. So we have some electronic wave function, we have a sum over all possible orbitals, and we move to the focus state where we have a 0 if we don't have any orbital, and we have a 1 if we have that orbital. And the goal will be to find what are the coefficients of these orbitals in particular. So what we can do is to write everything in the second quantization with the creation and annihilation operators. And this is an approximation, as you know. This only considers up to double excitations. We can consider more. And if we consider more, our quantum circuit will become more precise, but also more cumbersome. So that's why, as I said before, we need to find a way to find an approximation and at the same time not being too much big. So this is the coupled cluster single double model. For this kind of Hamiltonians. So let's see how can we put this inside of a quantum computer and solve it. So as I said before, we cannot compute the expectation values of the creation and annihilation operators. The only thing that we can compute with our quantum computer is the expectation value of Pauli strings. So that means that we need to translate all these Hamiltonian into Pauli strings, and we can do that using transformations like the Jordan-Wigner transformation. There are many others, but in the end, we have a recipe to translate the Hamiltonian into fermionic operators to spin operators that are the Pauli strings. So, okay, we have the minimization, so we have the objective function. We know how to measure that. The question will be, what do we use as a circuit answer? The hardware efficient one, the problem inspired one, etc. So with the original proposal of BQE, they propose a problem inspired one. So how can we use our knowledge about the structure of this Hamiltonian to find the circuit that probably will mimic it and solve it? So we are looking to something like that. So our unitary operator that will be the exponential of some unitary operator. And the wave function will look something like that, where the parameters, these T parameters, are in the end the coupled cluster operators and double cluster operators. And the coefficients of these parameters are the ones that we need to find with our quantum computer. But we have now a recipe because each exponential of a Pauli string, something like that. So once we translate all these parameters, these are annihilation operators, but we know how to transform them into Pauli strings using Jordan-Wigner transformation, for instance. So we will have something like exponential to y, sigma x or sigma y or something like that with some parameter in front. This is a rotational gate in quantum computation. So we know exactly how can we apply that in our quantum computer. So it will be a matter of translating everything. So we will have a big circuit, which will be something like this, rotational gates or 2-qubit gates that can also be applied from these kind of Pauli strings. So we have a way to do that, and we need to find these parameters here. the theta parameters. These are the coefficients that we need to find with our variational quantum algorithm. And we normally use as an initial state the Hartree-Fock approximation, because we know how to prepare it easily in our quantum computer. It's a product state, so it's not entangled, it's not complicated. Although people also try other kinds of states, like the 000 state, and let's see if we also arrive to the solution. So in the end, this is the BQE. So it's exactly like the variational quantum algorithm that I showed before, but here we use the unitary couple single double approximation. We can use other kinds of approximation. This is just an example, the one that was proposed in the original paper, but now people are studying other kinds of circuit ansatz that are also inspired by the molecule structure, or it's a hardware efficient one. So with that, let me move or prepare to with what kind of thing we did to improve the performance of the BQE. And we use quantum machine learning techniques. And I will just summarize very briefly what is quantum machine learning without entering into much details. So just to be clear, there are many kinds of quantum machine learning, because many people call quantum machine learning to different things. So just to be clear what I mean by quantum machine learning, we have two things that can be quantum: the algorithm itself. So are we using a quantum circuit for something or not? And the data. Is the data classical or quantum? So are we trying to figure out how to classify the points or an image or something like that? This is classical data. Or are we trying to learn what is going on in some experiment, which output is something that has a quantum origin? So that's why we have classical machine learning or quantum machine learning applied to classical data, or classical data applied to quantum, etc. So what I understand as a quantum machine learning is when you need a quantum computer to do your algorithm, and that's it. Doesn't matter if the data is classical or if the data is quantum. There are other people that call quantum machine learning to this part here. So you use a classical algorithm, so machine learning, but the data that you are trying to figure out has a quantum origin. For instance, trying to classify the phase transitions of spin models, etc. So just to be clear what I mean in the next slide. So as happens with standard machine learning, we have supervised learning, unsupervised, reinforcement, exactly the same kind of algorithms. So what is happening here basically is people are taking machine learning applications and translating into quantum and see if it has sense or not. So we are taking algorithms that are well known in machine learning and trying to figure out how can we adapt them to use a quantum computer, or if it's worth it, if not, etc. So for supervised learning, let me show how can we move from classical to quantum neural networks in a very pictorial manner. So we have classical neural network have mainly three parts: the input neurons, the hidden neurons that we can have here many layers that process the information that enters with the input neurons, and then some output neurons, and we compute some cost function that we need to optimize and minimize. That means fine-tuning the parameters that are here, okay? That are the weights and the biases of our network. In quantum neural networks, there are many kinds of, there are different proposals, but the circuit-centric one is the one that is more clear as analogy, which is something like this. We use quantum gates here to encode the data, then some processing gates here, like the rotational gates that I mentioned before, to process that data, and then we measure. And with the measurement, we compute the expectation value, which is our cost function, and we use a variational algorithm to find what are the parameters here that learn our cost function, minimize it, etc., depending of the algorithm. So how can we use this kind of idea to boost the BQE approach? So this, remember, the data will appear here, for instance, in the rotational gate. Instead of putting a parameter, I can put a parameter plus the data that I'm trying to learn. So this, the meta BQE algorithm that we propose, we realize that what is the true goal of the BQE algorithm, at least the true goal as it was proposed in the original paper. It was not to compute all this curve, but it was to find where is the minimum. So what is the minimal energy, the atomic separation that minimizes the energy. So what they did is to do all this simulation and see where is this minimum, okay? And they prove, look, we can use a quantum computer for that. Of course, And this will happen each time that you check quantum computing papers. This is a very simple molecule. It will happen over and over because we are using here, it was a 10-qubit quantum computer. So you can simulate that with a classical computer with no problem. So the idea of quantum computing, as I said at the beginning, is to prepare once we have a much higher number of qubits, so we can study molecules or properties or that are much more sophisticated than this. So this is a proof of concept in the end. So in the end, we are trying to figure out this part here. So can we try to avoid to compute all these points, because each of these points is a separate variational algorithm that takes time. You have to optimize all the parameters. You have to compute all the gradients if you're using gradient descent. So it's a lot of time actually to obtain all these curves. And in the end, you don't need all these points. So you are eventually only interested in this part. So can you avoid to compute this? So that's why we use quantum machine learning to try to learn the curve. So this is the overview of the algorithm. We start with a some parameterized Hamiltonian, which could be the one as mentioned before of a molecule or anything. We tested it with spin change as well. And the goal is to find the quantum circuit that encodes the ground state for all the parameters. So this parameter here could be the atomic distance, could be a transfer field if we are studying Ising-like spin chain. It could be anything that you are interested in. But the point is that you need to change the parameter every time. So you are trying to learn the ground state as a function of that parameter, as if you solve it analytically. So the standard BQE does individual minimizations, and then look, the minimum is here. Okay, I find the solution. This is my parameter for my solution. With BQE, what we do is take some points and try to approximate the solution to identify what is the minimum. So instead of using individual BQEs, we use only one BQE, but we take information for many parts of the system. So we have a training points. We use what is called data uploading strategy, which means that we introduce the parameters of the Hamiltonian in multiple parts of the circuit. And then we construct a super big cost function that takes into account different parameters of the Hamiltonian. And we want to minimize this loss function. So once we have minimized that, we have two options. We just change the parameter and scan for other ones, but this time we don't have to minimize again. We already have the quantum circuit, everything is optimized, everything is good. Or we can identify the minimum that is here. Okay, this is a minimum. So let's try to use a BQE that is more precise, but only in this minimum, not in all this curve. So this was the idea of the optimized meta BQE. And we benchmark it with H4 molecule. Again, it's a proof of concept simulation. And we check that in comparison with the standard BQE, our meta BQE was much more precise, and it requires less iterations, so it was faster. And we also study different kinds of encoding. So this is interesting, especially from a quantum machine learning point of view, which kind of circuits can learn better, etc. So this was the solution. We also try to check the initial state. If we use the Hartree fog, of course, the solution is better. We don't get trapped in local minima as expected, etc. So, okay, so this is an example of a quantum algorithm that involves a variational quantum algorithm, quantum computers, classical computers, etc. And also some knowledge about the molecule and about the computational chemistry methods. So how can we put everything together and help the future developers of quantum algorithms to use this kind of technology? And that is why we develop a quantum language that is called Tequila. And I would like to summarize this language as final part of my talk. So first, the quantum computer, this is more or less the structure of how can we program it. So this is the quantum device. Sometimes we have a quantum simulator because the device is too small, so we simulate everything and that's it. For instance, in BSC, we do that with our supercomputer and we can simulate up to 50 qubits or more. So in the end, people use both of them to check if the solution is similar, etc. So here, we start here, the problem definition, and we have to translate that into a quantum language. There are many of them. Then we have a quantum circuit, for instance, our parameterized quantum circuit. And this is parts, you normally don't see that. So you want to go from here to here. You don't care about this part. This part is done by the developers of the language. But there is some instructions here that are sent to the quantum device. So once we are done, we have to post-process the solution. And that means either we have the result or we have to start all over again because we are fine-tuning the parameters, as happens with variational algorithms. So this is the golden era of quantum languages. Probably most of you have heard about some of them. For instance, Qiskit is super famous, is developed by IBM. Cirq is the one developed by Google. PyQuil is developed by Rigetti. Kibov by Kilimanjaro. PennyLane by Xanadu. QSharp is Microsoft. So basically, each research group and each company is developed their own quantum language that control their machine or that controls other possible simulations or machines. But not only that, it's also the golden era of quantum software tools. So these tools, for instance, OpenFermi, maybe some of you, well, probably you are familiar with these ones, are necessary to implement a series of quantum algorithms that are related with different fields. And also these kind of languages, this for error mitigation in quantum algorithms, there are many tools and many other software libraries, but also classical tools. So we need to optimize the parameters of our circuit. So we use SciPy optimization, or we use other kinds of optimization subroutines that we already know from other fields in science. So in the end, we have a lot of things. We have to select one. We need to control all of them. And that becomes complicated for us. You have to lose a lot of time. For instance, if you want to check your algorithm in IBM machine, then you have to write everything again in a different language for Google machine, etc. So this is bad for benchmark and to compare solutions with different machines, and adds a lot of work to the researchers. So with Tequila, what we try to do is you program everything in one language, which is Tequila, and it's all of them are very similar. And then once you have this program, you just specify your backend. And okay, let's simulate or run it in QLAX backend, or let's simulate and run it in Qiskit using this device. And you don't have to translate everything to the new language. So each time that there appears other language, Tequila developers will just implement that in the bottom of the language, and you don't have to care about how can we put a quantum gate of this kind in this particular language. So this is the idea of Tequila, and we have a white paper, and the important part is you can find here the installation and documentation. Of course, it's developed by University of Toronto, so it's for researchers, and it's completely open source, so everyone can contribute. And there are some people actually that are not part of our group that are contributing to this language. This is the Tequila API. So again, it will be the similar structure as variational algorithms, but it can be used for other kinds of algorithms. For instance, we have a molecule and we need to write this molecule somehow. So me, as I'm not a chemist, I have no idea how can I obtain a Hamiltonian of a particular molecule, but there are some libraries that will help me. So it will be easy to translate that to a particular Hamiltonian. Then we can also find a way to construct an ansatz of our quantum circuit, for instance, with the UCC SD ansatz. And there is a function that does that for you automatically in Tequila. Then you compute expectation values. The objective function could be the energy, could be many things. So you can write any kind of objective function. And it goes to the quantum backend that could be a simulator or could be a real quantum computer. And we are working on introducing more and more backends. It goes to the optimizer, and here you have all these other backends, and you repeat the process or you stop your algorithm depending on what are you trying to do. Let me show a hello world example, and you can find more tutorials. There are many of them. There are tutorials of BQE, and there are tutorials of highly sophistications of BQE, especially for particular Bayesian sets, etc., for molecules. So imagine that you want to simulate the hydrogen lithium, right? Molecule. I never know how to do that say that in English, but sorry. HL molecule. With this particular basis set, you can select others, of course. So this is the output that you will obtain with Tequila and the orbitals that you will obtain. So you can, first of all, find the Hamiltonian by using the Jordan-Wigner transformation. As I said before, this is the part that we can measure in our quantum computer. So we cannot measure expectation values of anything that we want. We need to translate everything into Pauli strings. And we can use the Jordan-Wigner, that is the default one, but there are other kinds of transformations that you can also introduce here. So then we specify in the transformation, for instance, using the Rabi-Kitaev one. And in the end, there are many more, and you can also put your own. Then we have to select the active space. For instance, this is just an example, but in the end, it's something that is custom to you, so you can just choose whatever you prefer for your simulation. And then you can use classical methods, because in the end we are using a chemistry backends that can give you this information. So you can use that to compare the result of your simulation with the one that you will expect with a classical algorithm. And then this will be, for instance, an example of a big quiz. So here I'm writing the molecule, I'm making the Hamiltonian of the molecule, I'm constructing the circuit ansatz, I'm computing the expectation value, and then compute the energy using some classical methods, and then run the minimization using, for instance, the BFGS minimization method. There are many more, of course. And then let's print the solution. And this is just a proof of concept, but you will see something like this. So you see that it goes down, 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 down until it finds the final solution, which is the one that we expect by other kinds of methods. This becomes more and more sophisticated as you are trying to explore other kinds of molecules, as you can imagine. But the idea of tequila is you put everything together. So it only takes this space, let's see, to simulate everything. For instance, here we use one Trotter step, we can use more than one, etc. So let me finish my talk with some conclusions about this new era of quantum computation. There are many things to do. All the things that we have done are proof of concept. So we are not at the level of classical algorithms. So let me be clear on that. Not in chemistry, of course, but not in quantum machine learning either, not in any kind of method. But we are now figuring out that we have big quantum computers that start to be powerful, that are precise. There are many things to do from an experimental point of view, but we are working in that direction and everything is improving year by year. So we personally believe that we will achieve this new way of computing that doesn't come here to replace classical computation, but to work together with classical computation. So there are many challenges ahead, as you can imagine. From the theory side, we need to figure out which kind of problems can be solved efficiently in a classical computer. Some of them can, some will. So we need to figure out that. And also, what are these new algorithms? What are the theoretical limits of noise intermediate scale quantum computation? Because with ideal quantum computation, we know for sure which problems can be solved and which ones can't. But with NISQ, we don't know for sure. There are people trying to figure out these heuristic algorithms if they have some theory bounds or not. And then from the experimental side, which technology? I mean, there are many kinds of technologies, superconducting qubits, photons, trapped ions, etc. So we have many ways to build a quantum computer. It's not clear which one will be the best one. So this is one of the things that we are figured out. And in the middle, there are many things that we can do. Software tools like Tequila, benchmark methods. How can we compare the performance of these computers if they use different technologies? Try to figure out these practical applications. Enabling technologies, the quantum computer has many parts. It has electronics, it has cryogenics, it has many things. So we need new materials to build the qubits in the first place. So in the end, there is a lot of work to do. And there are many things that we need to figure out as a society or scientific society in this sense, which is, first of all, people. This is a field that has exploded recently, and there is not so many people that work on quantum computing. And especially there is not so many people from different fields than physics that work on quantum computing. And now we need that, because as a physicist, we know that we have this device, we know how the technology works in theory, but now we need other people that comes and say, okay, I have this problem that I can't solve with classical computation. Can we try to figure it out? How can we solve it with quantum or not? So we need this kind of input, and we need people from other backgrounds to enter to the field. Then we need these enabling technologies to build the devices in the first place, because if everything is developed in the theory side, we will never have the quantum computer. As I said, we need this interdisciplinary, we need a lot of people first, but then people from different backgrounds. And finally, we believe that for that, we need quantum as a service. So quantum computers so far are in big companies that they give you access in the cloud if you pay for it, and for some small devices, it's free. Or they are in startups or in big universities where they have a laboratory and they build the quantum computer there. But these are very new technologies. So normally these labs, people are working on improving the individual qubits, improving the operations, but not trying to figure out applications because they have other things to work on. So now it's time that quantum computers arrive to other people without having access directly to a laboratory, as happened in the last years with small prototypes of quantum computers. And for these reasons, we have this kind of project that you have heard about maybe in the news, which is Quantum Spain. And the idea is this is not the only project that exists in Europe. There are other projects of these similar characteristics. This is the only project, though, that organizes as a network, because the idea is we will have a quantum computer in 1 year in Barcelona Supercomputing Center, and the access will be exactly the same as the other supercomputers in the rest. So if you are familiar of how this works, is exactly the same. It will be another backend, another computer that you can ask for access. And the idea is to do, of course, research, because this is a very new technology, so we need to figure out many things, as you know. But starting, to transition from having these computers into our labs for research to moving it to a service to other kinds of both society, of people from different backgrounds and interests that they want to test if it has sense or not to use a quantum computer. And also we will have a super big training program. So it will keep you updated, because there will be many initiatives, of course, here in Barcelona, like hackathons and similar and courses, etc., that will be free, of course, to try to move this technology from physicists and mathematicians to other kinds of researchers. But more info about this project, I will present it in this other talk. And that's all. I would like to acknowledge of all my collaborators in the Matter Lab. I miss them very much. So it was a weird 2 years of postdoc, because it was 1.5 was during COVID, but we did a lot of super cool things, and it's a very nice group to work on, because it's super multidisciplinary. I was part of the quantum computing one, so most of them were physicists there, but you have access, and you can talk with people that are, for instance, chemists, and they have a lab there. So I learned also about many things that they do in developer of new materials and automatic discovery of materials. So it was super nice. And that's all. Thank you very much. And thanks for the invitation.
Okay. Thank you, Alba. Very nice talk on quantum computing. I think that we have learned a lot. Now there's time for some questions. Both here are also the people via Zoom.
Okay, so at the very beginning that you had the slide on quantum computer, and basically you had two parts, like the classical and the quantum. But I thought actually that this was for like to my understanding, I thought that this was for NISQ devices. But then when eventually reached like the actual quantum computer, that everything was going to be quantum.
So, sorry, I didn't hear you.
Yes, so
it's
I thought
not only for NISQ, you mean?
Yes, so I thought that was for NISQ devices, but it seems that you think that this is going to be for the actual quantum computer, that not everything is going to be quantum.
Yeah,
so
exactly.
Is that the case?
Yeah. It's sometimes, we talk about quantum computer and it's like, yeah, everything is quantum, and it's not. And the main reason is you cannot control and access quantum physics with classical physics, because we are classical. So we need a way to control this machine and to read the state of the qubits, the wave function, operators, etc. That's why we need a classical computer. We need to send the instructions. So what happens is I have my quantum computing device that is controlled with classical electronics. So with electronics that send, for instance, for superconducting qubits, it's microwave pulses that alter the state of these qubits. And to write that, you need a classical device like a laptop that sends the instructions to this device. So in the end, you need a classical computer. Maybe you don't need the classical algorithms. You need the classical algorithms for these variational quantum algorithms, for instance. Maybe for others, you don't need that. It's only to send the instruction and that's it. But you will need a classical computer next to it for sure, because you need to find a way to communicate with the quantum computer, and you are classical, so you need to translate your classical world to the quantum one.
Yeah, okay, yeah, makes sense. And then another quick question. So about like the applications that you mentioned, so basically for the moment, it seems that most of them are in the quantum chemistry field, but do you have any guess like which other field maybe will be possible, or any other idea?
The quantum chemistry was basically because the BQE was one of the first algorithms that showed that noisy devices can be used for something, and it was focused on chemistry. But now BQE is also used for condensed matter physics to study different phases of spin chains, etc. And then you can use the BQE was just the beginning of this family of variational quantum algorithms. And many quantum machine learning ones use this kind of algorithms. So in the end, anything that you can think about to solve with machine learning, you can think about solving it with quantum machine learning using this kind of algorithms. Or there are other paradigms in NISQ. I didn't mention that. These are, all the time I was talking about what is called digital quantum computation. So everything is written in quantum logic gates. But there are other paradigms that are analog quantum computation. So you prepare the system and let it evolve with some field that drives it, etc. And people are using this kind of computation to solve optimization problems. So in the end, you are trying to find where is the minimum of a very complicated function or combinatorial problem. And it's a good way to let the nature figure it out, where is this minimum. So these are also one of the big applications of quantum computing that people believe that will lead to some advantage.
Great, thank you.
Just one sec. There's a question here about Albert Ruiz. Thanks for the very nice talk. Could you explain a bit more about how quantum computer can be simulated with what errors, assumptions, and how costly it is?
First, to simulate a quantum computer, I mean, rawly, let's say, without considering anything or not doing it very efficient, you need a vector of dimension 2 for each qubit. So, and use Kronecker product. So you have a qubit is a vector of how many 0 and how many 1 you have in the end. You can put that in your algorithm, in your computer. And then if you want to study the state of 2 qubits, you do Kronecker product of these 2 vectors. So you have a vector of dimension 4, dimension 8, 16, and so on and so forth. That's why it grows exponentially as expected. There are some very clever techniques to simulate quantum systems. For instance, tensor networks, they are used, I mean, they are well known for many years. And now people are trying to use tensor networks to simulate not only quantum systems, but also to simulate quantum circuits directly. And for instance, we are doing that with our supercomputer, putting this kind of super big tensor network in the supercomputer. And for assumptions related with errors, that's really hard because there are ways to introduce these errors manually, let's say, like let's assume that there is some probability of this qubit to flip from 0 to 1 and this kind of things. But these are very weak assumptions somehow, because then you go to the device and it's not related with that at all. So it's also a big field of study. How can we simulate the noise and understand it better to improve also the quantum computer? And you have to solve things like the Limbat master equation, this kind of stuff, to see how is the evolution of this quantum state. Because in the end, a quantum computer is a quantum system, so you need to use the tools that we normally use to simulate quantum systems. But it grows exponentially. So now in your laptop, you can simulate up to 16 qubits, maybe 20 if you use some techniques. With supercomputers, you can go up to 50. I mean, now it's a kind of race. It's very, it's curious. With these claims of quantum supremacy, with 50 qubits at the beginning with Google, there were a lot of people from computer science and from HPC world that they say, wait, we can do that. And we don't need 1,000 years as they claim. And there were some claims, I mean, not only claims, but experiments later that show that, yeah, they can simulate the full experiment in, I don't know, 3 minutes, 4 minutes or something like that. But how many energy and cores they require to do that, it was a huge simulation. While the Google experiment, it was seconds, and it requires a super few amount of energy because these quantum devices doesn't spend energy almost. So this is another quantum advantage that people sometimes forget, that quantum computers are energy efficient. So even if we can do the same with quantum and classical, maybe we don't require too much energy to do the same.
Thank you very much for the presentation. I have one question. At the beginning, in quantum computing for electronic structure methods, the goal was to have linear scaling for full CI. This was the thing that the people sell. However, now it seems that this variational unitary coupled cluster calculation is the approach that most of the groups are proposing for the electronic structure. What do you think in the future? The people will move to more sophisticated, or they will follow with this couplet cluster approach?
I believe people will move, and they are moving to things more sophisticated. Even our group, people that are the chemistry part of quantum computing group, are working on other kinds of ansatz and circuits, because what people realize is BQE was a very nice and elegant idea. But then when you are trying to encode molecules that are more big or you are trying to be more precise, the system starts to grow in a way that you cannot handle or put into a quantum computer. So you need to find a way to codify the information in a completely different way. Or if you are considering more basis set, etc., the scaling could be bad. So it's not polynomial anymore, or it could be polynomial, but if the term in front of it is super big, it's not useful at short term. So what people are trying to figure out is other kinds of ansatz, other kinds of encodings, and ways to handle this BQE. And the gradient methods is also could be also a thing that is not super good, because if you have a lot of parameters, you need to compute a gradient for each of them, and that means a lot of extra measurements in your quantum computer. So that's why people are trying to reduce the number of parameters as much as possible and trying to find a way to optimize them. So it's a very active field precisely for that, because they realize that it was not as nice as expected when you start to think about things that are more complicated. But there are some I cannot explain because I'm not familiar with them, but there are some techniques developed also in our group that they find a way to measure only a few qubits and already reconstruct almost the whole wave function or some of the measurements. So it was a very efficient way to use different active spaces, etc. So it's a very active field in that sense, but not anymore the original one. So now people are moving to things that are different and more sophisticated.
And to add, for instance, periodic boundary conditions for the calculation to describe materials instead to have just discrete molecules, because most of the examples that you can see in the papers are just molecules. However, maybe the community are more interested in materials that are you have periodic boundary conditions. This is easy to introduce periodic boundary conditions in this kind of approaches?
As far as I know, it's not. And the reason why we are working with molecules and simple molecules is it's the thing that we can access with our simulations. If we start to introduce things that are more sophisticated, we cannot even simulate that, because we can only simulate up to 20 qubits with our laptops, 40 or 50 with supercomputers. So it's not clear how can we, in the first place, test if it works or not, because we cannot even simulate it, and our quantum computers are not as big or good to do that yet. Although I believe that there are people trying to work on theory on that. So let's be prepared for that. And that's why this NISQ era is about this, like, let's try to prepare, but at the same time, we cannot do anything that we want, because once you start to use methods more sophisticated, you have not enough qubits. So it's complicated. But if you see simple examples, it's because we cannot do things that are better with the resources that we have right now.
Okay, and final question. Concerning the technologies, I read, for instance, that trap ion is I guess the best technology because the error is smaller than, for instance, with superconductors. Really, the difference is very important. Do you think that, for instance, in our field, in electronic structure calculations, that will be an important point that probably the people will try to perform the calculation in these trap ion systems that instead to use superconductors?
Well, this is a big discussion, because I will say that it's superconducting circuits, which is the technology that I'm more familiar with. But in the end, what happens is, I mean, for us, theoreticians and people that work for application, it's not our work in the sense that it doesn't matter. You will use the quantum computer that has the less error rates. And it could be trapped ions, it could be superconducting circuits, it could be photons, it could be many. You don't care about that. So it's not about the technology itself. It will not solve better your problem. What will solve better your problem is that the quantum gate is better and it has better fidelity or less error or whatever. It's the only thing that you should care. Although for some problems, you need that all qubits are connected, or the more connections, the better, because that means that you will need less quantum gates. And there are some technologies that it's easy to connect the qubits. For instance, with trapped ions, you put two of them together and you can make them interact and so on and so forth. While for superconducting circuits, you build a chip and you cannot change that afterwards. But at the same time, trapped ions require more time to perform the operation. Superconducting circuits are super fast. Trapped ions, it's difficult to install them outside of, as far as I know, outside of a lab. So you have the trapped ion computer in your lab, but move it to another place, it's hard, which could complicate the things at the long run because you cannot install it in places like supercomputing centers. While the superconducting one, it's easy to move, etc. And the scaling is hard. So with trapped ions, the quality is super good, but the scaling to more than 20 qubits becomes more and more complicated. I mean, you can put a lot of ions, but you cannot maybe use all possible operations of them. So this is something that people there are working out, trying to figure out. Why superconducting circuits you can have more, but maybe the quality is not as good. So it's not clear, and to be honest, that's why all policies related with quantum computing in general, in Europe in particular, shouldn't only invest in one technology, because you never know. Many things could change. I mean, it's kind of a race, and sometimes one technology is better than the other, but everything is so new that we don't know for sure. Maybe it will be an hybrid of both technologies. We'll see.
Hi, so thanks a lot for your presentation. So I have a question for the parameterized quantum circuits that you showed at the beginning. So in order to solve a given problem, you have to optimize the coefficients of the circuit. My question is, this optimization of the coefficients is problem dependent or system dependent? So that means that for the optimization problem, you have a set of optimized parameters that more or less succeed in any optimization, or for every molecule that you want to optimize, depending on size, number of degrees of freedom or whatever, you have to re-optimize those coefficients and redesign the circuit to effectively solve the optimization problem?
The thing, depending on which circuit ansatz are you using. So if you use the hardware efficient one, which is the heuristic, you use the same for everyone. So it's time that you change your Hamiltonian, you need to find the new parameters again. But unless for some reason that you are super lucky, you are already close to the local minima with the initial random initialization, you will require the same amount of iterations. If you use the problem-inspired one, it depends, because it depends on the Hamiltonian. You will have one circuit or you will have another. It could be that in some molecules you have a lot of parameters to optimize. In others, you have a few parameters to optimize. So it depends. But if you have exactly the same ansatz for all of them, the amount of optimization will be the same order of magnitude. So it will not change too much. What will change is once you define the circuit in the first place. If it's problem-inspired, it could be super simple, or it could be complicated and that requires more optimization, and etc. And there are some people, I don't know if you mentioned that for this reason, but there are some people working on trying to adapt with the optimization. So it depends on the value. Let's add another gate here, or this kind of things. These are other ways that people are trying to figure out to improve the performance, especially to go closer to the ground states, to not get trapped. So as I said in that slide, what happens when you fix an ansatz is you cross your fingers that your solution is in this Hilbert space that these ansatz can explore, because you cannot encode a full unitary operation once you have a lot of qubits, but you don't know for sure. So it could be maybe you are trapped in some local minima and there is no way that you can explore the solution space. That's why maybe if you iteratively add more gates or etc. could be a way to find a solution.
That was the other question. Is it possible to design an adaptative
No, it's not impossible. You can do that. Okay. It could be more or less complicated to figure out how, but there are people working on these kind of things.
Thanks a lot.
In the variational algorithm that you explained, where does the noise influence, in a sense? I mean, if you had, in the limiting case of zero noise, you would still need to optimize, right?
Yes.
Because the parameters are not optimal. So, and I guess that at some point, this noise is what comes from the quality of your hardware, no? So, it does play a role. If it's too large, probably there is nothing to be done. No.
Exactly. Actually, this is a good point, because these variational algorithms work I mean, the same way, even if you have a perfect quantum computer, because it could be, okay, you have a perfect quantum computer, simulate, prepare the ground state of this molecule. How? I mean, you need to find the unitary operation in the first place. So it could be a way, and that's why quantum computing and classical computers should work together to find a solution. What happens in noisy devices is that sometimes noise is too high. So even if you have this nice type of algorithm that technically adapts to the noise, it's not enough. And the problem is not with the gates in particular, because you will always find the parameter of the gate that is suited for this particular device. It's the coherence and relaxation. So what happens with qubits, if you can only apply the computation during a fixed time, and if the qubits start to decohere and interact with the environment, etc., you lose all the quantum properties. So you are completely lost. You cannot do anything. And that's what happens. If you have too much noise, you don't have a truly quantum device. You have something that is interacting randomly with the environment. So that's why it's so important to have very low error rates for gates, but also long coherence times, or maybe not long, but the amount of gates that you can apply in the coherent time that you have as large as possible. Because there are some technologies that their qubits last, I don't know, 1 millisecond maybe, which is a lot of time. But then the gates also take the order of microseconds, so you cannot apply many of them. While others, maybe they last much less, but the gates are faster. So it's always this trade-off. But yeah, if you have the coherence, you cannot do anything at all. That's why some of these quantum devices, sometimes they say, oh, we have 100 qubits, we have 60 qubits, we have many. But then if the coherence times are super short, you cannot do absolutely anything with them.
Thank you. Any other question? On the Zoom. So thank you, Alba. But just a comment, I really like the comparison you've done of the machine learning, the classic versus the quantum, because sometimes you read a paper and quantum machine learning is misused because they are using the classic machine learning.
Well, there's always the people from these kind of papers, they actually at the same time they will propose the both of them at the same time. So that's why they say, no, quantum machine learning is ours, not yours. And there is this kind of internal war. But that's why it's important to let clear, okay, this is what I understand as a quantum machine learning.
Yeah, so thank you very much. So thanks for having come and for having shown us your wall, let's say. So thank you very much.
Thanks.